Hello, everyone, and welcome. This is going to cover chapter 17. So, we're going to get into corrosion and design parameters with regard to materials. This is an important chapter to understand. We're going to be doing this across all of the different sections of the materials classes, so everyone's more or less in the same place at the moment. I wanted to cover and make sure that we had enough detail in this to be able to hit all of the key points, but also show some examples of some of the problems. We'll try and get through this as expediently as possible, but this should set you up to be able to continue working on the homework as well as some of the projects that are ongoing. And at the very end, I'll talk a little bit about some of the Ashby plots and things for material selection specific to the METs, but it'll benefit the MEs that are looking to do the materials website as well. So there's a lot that goes into the applications of this particular chapter because corrosion tends to be pretty important. Some of the Ashby plot aspects become relevant even more so in the chapters that we're going to be getting to in terms of their use and application of polymers and non-metallic materials. So hybrids, composites, all of those sorts of things become very, very important. Ashby plots help to generalize materials behaviors in a couple different manners. And so we'll talk about those at the end. For corrosion, this is a huge problem in a lot of areas. We're going to look at a corrosion map of the country as a whole to see what different regions are ranked in different corrosion grades, and they have different rates of corrosion. Some areas are extremely fast, some areas are extremely low, but any type of metal that corrodes is part of what we're talking about today. So we're going to touch on how does corrosion occur. We're going to touch on which are most likely to corrode, what environmental parameters are going to be affected, as well as how do we actually prevent and or control the corrosion and what things affect the corrosion rate. So these are some of the things that are going to be playing into what we're doing today. So here's what we're going to be doing in terms of materials. Let me make sure we've got, yeah, there we go. The cost of corrosion is going to be very, very high, on the order of 4 to 5%, as of a report that was done in the mid 80s. So some of this is again fairly out of date, as a lot of textbooks tend to be. Information from 20-30 years ago that was relevant. I suspect it's probably a lot higher now, especially with inflation. I think 400 billion is about a gazillion dollars now. So thanks the folks that are responsible for that one. Corrosion is the altering in a destructive manner of a material. It's no longer able to perform its original function to the same degree. So what we see here is an attack of rust on a material, in this case steel, and rusting of automobiles and equipment, all different types of metallic structures, especially ones that their coatings have burned off or whatever, have been worn off or eroded over time. Those are able to rust. Interestingly, in a material like that, once it starts rusting, yes, it is a continual process of rusting, but the actual surface corrosion rate slows down, and we're going to talk about that later on. So when you see a lot of high-end buildings like Starbucks building a new location, and then they immediately rust the structural steel in their super modern industrial design, that's actually a corrosion prevention strategy. So preventing corrosion by intentionally causing corrosion. Don't worry, it'll all make sense later. Or some of it will. We'll find out. So somewhere on the order of 4 to 5% used to be the standard from the gross national product as far as the cost of corrosion every year. And there's a lot of different factors that go into estimating that, but we won't get too much farther into the cost factor. Just know that it's a major problem. If it's in the billions of dollars or hundreds of billions of dollars range, it's a significant problem. This is fundamentally an electrochemical process in all metals, all alloys, everything that corrodes. This is the thing that's actually happening. So this corrosion happens with two sides. There's an oxidation and there's a reduction side. So remembering back to the Gen Chem things that you guys have almost certainly forgotten, remember Leo Gur or oil rig, depending on whatever mnemonic device is of your preference. Oil rig is oxidation is loss and reduction is gain. Leo Gur is loss of electrons is oxidation, gain of electrons is reduction. It's the same principle, whatever mnemonic device helps you to recall the particular details of how this operates. So in the case of zinc and just about anything else, zinc is able to give up these electrons and sit comfortably in a lower energy oxidized state, having given up those electrons. This is part of the reason why we use zinc in all kinds of galvanized steels and things of that nature, because it freely allows for giving up its electrons rather than the iron having to do so, which prevents some of the further oxidation. And we'll look at some of the strategies and layering that goes into this. But the corrosion of zinc in an acidic solution, so anything that has a lot of protons that are coming in trying to strip those electrons away because of the charge imbalance, remembering that nature abhors a vacuum, all of those things are trying to rip those electrons off of the surface material. So this is an aqueous solution in the blue that's trying to take away the electrons and eat away at the material of the zinc, in this case the acidic solution. So this is part of the reason that over time, even zinc oxide panels are things that can erode over the course of time. They can rust just like regular steel. It tends to be a little bit slower process, but you get the general idea here that those two hydrogens bring those two electrons in, those two protons, and then it forms hydrogen gas. So that's what bubbles off of the surface. And we'll look at an example or a demonstration of somebody that's put together the lab experiment from one end to the other of building an entire hydrogen electrode that I think will help kind of tie everything together. It won't all completely make sense, but it will at least demonstrate for you how to, from scratch, be able to build this electrode and understand how we can actually measure some of these different electrical potentials, and then we'll talk about what we do about these corrosion problems after that. So the reduction is a solution, often something like dissolved oxygen or some other species chemically that has these free electrons that is able to grab onto those protons. So they have free electron pairs in the solution bumping around, and what that does is that allows for a site of attachment for these hydrogen atoms. So when you add in the presence of an acidic solution, so if you have oxygen in the presence of an acidic solution, you have all the things on the left side of this. If you have the presence of oxygen, what you can get is those electrons being a carrier to help form water droplets, so H2O or water vapor, in an acidic solution. In a neutral solution, in the same thing, in the presence of oxygen, you can have water combining with the oxygen in order to then help break apart or strip off hydrogens. And what that does is free up an electron. So in the basic solution, you have hydrogens being stripped off of water, leaving OH ions or negative ions. So what these are trying to, they're then floating around in solution with an extra electron waiting to steal hydrogen from somewhere else. So that's what's happening in a basic solution. So acidic solution, you are picking up those electrons and forming water. So you're taking, essentially think of it as taking energy into the process. In the other case, you are still bringing in electrons, and you're now creating a lot of these hydroxide or OH ions that are now going to be running around looking for free protons. So each side of them is going to behave differently. Different metals behave differently in acidic versus these neutral or basic solutions. So we're going to pay attention to some of the details that come up there. So corrosion is one of the outcomes. And this looks like you have two electrodes, you have some kind of voltmeter, or it can even be a load. In this case, we're talking about between two solutions that have a galvanic pairing, and we have the electrons being stripped off, and we have manganese ions. Or these are just representing metal, so it's not actually Mn manganese. It's representing some sacrificial metal that's being eroded. So the ions are going into the solution on the one side. You have some kind of a salt bridge connecting the two in order to allow the exchange of ions. The free protons from the acidic solution are attacking the platinum surface, stripping off the electrons from this process in order to plate this first side and pull away the hydrogen gas. So hydrogen gas is forming as these electrons are reaching the surface. So there's really not as much happening to the platinum, but this sacrificial metal is eroding. And that's a technique that we use for corrosion control later on by sort of reversing the flow of electrons and forcing this to take place. So there's a standard electrical potential, something that you may remember vaguely from your Gen Chem process. But what it is anything that is negative anything negative relative to platinum is going to be anodic relative to platinum. And so we'll talk a little bit more about the roles of those things as well. Anything that is going the opposite direction, so taking the ions out of solution and plating the metal, is going to be going the opposite way. So you're taking the electrons, still running it through some kind of meter, some measurement device, or maybe you're driving this on purpose with a difference in electrical potential. So you're plating the metal that would otherwise be corroding. The hydrogen gas is being stripped for its electrons, and you're increasing the acidity of the solution. So that's also one of the possibilities. So this metal is acting cathodically compared to the platinum, and that gives us a positive side potential, or V naught for the metal. So these are the standard electric potentials, and these are different based on just the atomic structure and makeup of the materials. So we're going to look at a chart that's going to help us to understand a little bit better about what's going on in these. And then we'll spend probably a lot of the time toward the end in the actual problems, taking a look at how do you understand these things, because these are trying to be compared at a reasonably standard set of parameters, all at 25C. Everything is a 1 molar solution, trying to equalize everything else. If you imbalance a bunch of those, you create other driving forces and driving factors that you guys have talked about in the context of Gen Chem, but haven't spent a whole lot of time thinking about. So let's take a look at this.
Welcome to this video on the standard hydrogen electrode. In order to produce this electrode or half cell, we need to generate some hydrogen gas. And so we've got in this flask on the left some sulfuric acid reacting with zinc granules. It's got some copper sulfate in it to make the reaction faster. You can see the hydrogen gas coming out of here at the top of the flask, and it's passing through the orange tube, through an aspirator containing potassium manganate 7, which is just oxidizing any sulfurous gases that have been produced, and then over across through the pipe and now into the main setup, which we can see here. In the beaker here we've got some 1 mole per decimeter cubed hydrochloric acid, and then bubbling into the beaker through this pipe at the top is some hydrogen gas at a pressure of 1 atmosphere. And inside this housing we've got a platinum wire, and at the bottom we can see some porous platinum. That's going to be taking the electrons out of this half cell in a moment. In order to use the standard hydrogen electrode to measure standard electrode potentials, we need to connect the standard hydrogen half cell to a second half cell. And here I've chosen a half cell between zinc 2+ ions in aqueous solution. So we've got a 1 mole per decimeter cubed solution of zinc sulfate here. And we've also got a piece of zinc. So that's going to be an equilibrium between zinc and Zn2+ aqueous ions. We want to know the standard electrode potential of that. We've connected them up with a salt bridge here, which allows the passage of ions between the half cells. And now we need to connect them up to a high resistance voltmeter in order to actually measure the potential difference between the two half cells. Now when we do this, we're always going to connect the standard hydrogen electrode up to the negative terminal, and the test half cell always goes into the positive terminal. And the minute I do that, I can see the voltage pops up at minus 0.72 or minus 0.73 volts. So here's another example of the standard hydrogen electrode in action. This time I've got a 1 mole per decimeter cubed solution of copper sulfate on the right, still the same standard hydrogen electrode on the left, and I've also got a piece of copper. So this is the equilibrium between copper 2+ and copper metal. In a moment I'm going to turn on the voltmeter. If I turn on the voltmeter now, I actually get a reading of 0. And the reason for that is because I don't yet have a salt bridge connecting up my two half cells. And this is really important. So what I've got here is this. Here's the salt bridge that I've just produced. Bit of chromatography paper soaked in saturated potassium nitrate solution. And I just pass that between the two using tweezers. Just make sure it's in contact with both solutions. You sometimes need to bring them quite close in order to make that happen, but I think it's now in both. And then now if I turn on the voltmeter, I should instantly get a reading, this time of 0.31 volts.
So what we have to look at now is what's called the EMF series. So what this does is gives us an idea about the electromotive force. That's what the EMF stands for. The difference in electromotive force. So how strongly does a metal want to move in one direction or another, toward the cathodic side, toward the anodic side? Where does it want to drive constantly? Iron is a pretty strong driver on the anodic side. We get more and more and more like potassium. So it should be of no surprise to you, for instance, that the body, the biology, naturally uses the pairing down here, sodium, potassium, all of these sorts of ions. That's why it's really important to have all of your vitamins and minerals and eat your Wheaties all morning and all those things. Is your body has a sodium potassium pump system where it's changing out these ions back and forth across different membranes and concentration gradients and things. They have very strong charges relative to everything else. In fact, significantly stronger than anything on the cathodic side. So very, very strong signals, meaning they can get a little higher signal throughput per net energy put in. And that's why nerve transduction works in a biological system, and you don't have to be hooked up to some kind of a car battery all the time in order to just be able to have nervous function and detect things like you would if you were if your nervous system was based on copper or some other silly thing like that. So there's always a reason for something specifically, and this standard potential table tells you, this EMF table tells you why those are being used. Their very, very strong polarized nature allows for those things to be very, very important, as well as zinc and some of the others. Certainly iron is important too in the biological context, but these are hugely different. So there's a reason that sodium, potassium, magnesium are often used in materials, and because they're so different in their EMF than some of these other materials, especially something like copper, putting those things together can give you a net difference in order to have a fairly large potential. So there's a lot of things that go into that. A lot of battery technology is fundamentally dependent on this chemistry that exists. So you can't like go outside of the electromotive force to create a battery. You have to work within these constraints and the chemistry that's available. So this is why we haven't solved the battery problem, and the notion that everybody's driving electric cars in 10 years is just nonsense. You're fundamentally constrained by chemistry and the weight of all of the reactions that you have to carry around in order to generate the energy. You can't just generate the energy without going something much more extreme and destructive and much more difficult to contain, like nuclear fission on a small scale or something. So if everybody's driving cars in 10 years that are powered electrically, they're powered by small nuclear reactors rather than just batteries. This is the reality of the chemistry. Everybody else that tells you something different is trying to sell you something. So we see some corrosion happen when there is a galvanic pairing, meaning there's a difference between the two. So nickel cadmium, in this example, is a common pairing for batteries for this very reason. You can have a small voltage difference between the two, in this case about 0.15 volts for their standard potentials. So that means in an ideal scenario, you can have solutions both of the cadmium and the nickel with the second state ion, so 2+, at 25, and at room temperature it is naturally going to cause a current. The cadmium corrodes, and the nickel gets plated by the solution. So you see the erosion of the cadmium and the plating of the nickel from the solution. Once you deplete either side of this, so if they're unequal in volume, these reservoirs, that current no longer flows, because once you have no more cadmium to degrade or you have no more nickel to plate out of solution, the battery is spent. And so this is what happens to our alkaline batteries. That's what these are. So they're on the cathodic side. They're alkaline batteries, very common. There's a lot of other chemistries involved, but the idea is if you have a difference between those two, you can have corrosion naturally take place at room temperature. It goes faster at elevated temperatures, and so that's why batteries, especially in things like electric cars and hybrids and things, they don't have nearly the same amount of energy output as they would in warmer temperatures, in cold temperatures. So you reduce significantly the range and utility, just like the batteries for your power drills. If you try and use it when it's 20 degrees outside, you're going to have a lot lower performance. You're going to have a lot less useful time frame because of the chemistry that's involved. Lower temperature, lower stored kinetic energy, much more that it has to overcome, so a lot more energy gets spent effectively in trying to rewarm the battery itself. And so this is why trying to keep things at the right correct temperature is part of what allows for efficiency. And that's why electric cars just sitting in a parking lot consume their own energy, is trying to maintain all the right temperatures of all the different components and things, so they can burn down their entire battery sometimes in as little as a couple weeks sitting in the driveway, which is just ridiculous. You can also see examples of corrosion facilitated by something like a grapefruit. Most people aren't sticking different metals in their grapefruits and hooking them up to voltmeters, but that's because most people aren't Mr. Wizard, which is a thing that predates most of you, so that's okay. Corrosion in a grapefruit starts with an acidic solution, so any kind of citrus fruit this technically works for. Anything that has free acid, so limes, lemons, oranges, grapefruits, tangelos, whatever variant of something you can find. There's not nearly as much liquid in them, but you could do the same sort of corrosion experiment in a lot of different sorts of peppers, so long as they were still sufficiently moist. The idea is anything that has a significant amount of free acid, especially something like a jalapeno that's very moist. That might be a better example than some of the much drier chilies and things of that nature. Especially the small ones don't tend to have a lot of moisture, so they're very concentrated. A lot of acid, little moisture, high concentration, hence the strength difference, partially in the level of acidity and how hot the peppers are perceived to be. So very small peppers, watch out, concentrated acidic content. Now you know why chemically. So adding the two protons and the two electrons together gives us the hydrogen gas at the site of the cathode here. So the electrons are passing from the anode, so the thing that's almost always being sacrificed. The electrons are being stripped away. Those ions are leaving the material, so the material is being eaten away by the acid. So the hydrogens are literally coming in like bullies, stealing the electrons, leaving these ions to float free in solution. The hydrogen is coming to the other side and taking those extra electrons because that's what protons are. They're just electron thieves. So they're working on both sides of this equation in order to steal electrons for themselves. So they're working to steal on this side, working to steal on this side, and selfishly keeping it for their own gassy purposes. So the oxygen that's present, along with some of the additional protons and some of the electrons, are also forming water as a byproduct. So these are the two reactions that are happening at the reduction side. So gain of electrons is reduction, reduction of electrons, reduction is gain of electrons, oxidation is loss of electrons, so electrons being stolen from that side. So whatever mnemonic device helps you to remember, this is the fundamental process that's happening. So the concentration and temperature effects we've alluded to, but you can see some examples of these. So looking at, for instance, the same nickel cadmium example, think of a simple like a watch battery or something. The lithium ion batteries are only a very recent advent of technology. A lot of things have been nickel cadmium, nickel metal hydride for rechargeable batteries going back a long time. So this kind of 0.15 volt per cell difference is much more common than it used to be. So some of these batteries are fairly low in terms of overall voltage and definitely low in amperage that they can produce, but they don't have to be extreme in order to run really, really small electronic loads. When you change temperature and concentration, you start looking at this equation. So the difference in standard potential now minus this adjusting factor. So we're moving from the difference in the potential is the standard difference, but now we include another adjusting factor or correcting factor, RT over NF times the natural log of X over Y. So X being concentration on the anodic side, the Y being the concentration on the cathodic side. So what we're trying to do is understand how that ratio impacts it. N is just the number of electrons per unit of oxidation or reduction. In this case, 2, because of what we've established as the states here. These are +2 ions, so we have 2 electrons moving from cadmium to give us a +2 ion. So that's where we get the number of electrons. And Faraday's constant, 96,500 coulombs per mole, such that we plug that into our equation to understand we reduce this voltage difference by increasing temperature. So really, really, really hot battery is going to have a lower potential than a slightly colder battery, but equally increasing the concentration in X. So the top fraction, so increasing the concentration on this anodic side. So if we overload this side, or if we decrease this side, if we decrease the cathodic side concentration of ions, that's going to reduce the ability for us to move the electrons and actually plate this cathode on the surface. So there's a couple different factors that go on there. Depending on what kind of ions they can form, sometimes N is going to be bigger, sometimes it's going to be 1. There's occasions where N will be 3, but most often it's going to be 1 or 2 for most solutions that we're going to be working with. There's also a galvanic series to understand what things are inherently more cathodic, so things that are less and less and less reactive as you go up the scale. Platinum sitting at the top, that's why we use it in a lot of electrodes. Gold is just a really great material overall. Not good structurally, but for a lot of applications where corrosion is present, it's just a one material that does a lot of things actually really well, especially in terms of electronics and some of the capabilities. So graphite, slightly below that, very inert. Titanium and silver, things like silver you see go ages and ages without being heavily tarnished. They can be tarnished, especially in the highly corrosive environments that we'll talk about later. There's stainless steels, so passive stainless steel. You can have active stainless steel, but passive is more common. You have to do a bunch of things in order to make stainless steel active. So in a lot of cases, we're not seeing that as the native state of the material. So nickel, also, reason we nickel or copper plate things before doing a chrome plating or some other material is we're trying to step it up gradually from an active material. A lot of steels and cast irons down here, we plate them with copper or nickel, sometimes back and forth, to get them up into this range, and then we do a stainless plating or some other material, titanium, some other coating, chrome, all sorts of things like that. So we step them up the process in order to get them to become more inert. And that's why very old chrome plated items may have resisted corrosion for such a long time. Things that are much more active, so much more prone to corrode, tin, lead, cast irons, steels that are uncoated. Aluminum actually corrodes very much. We don't think of aluminum as being something that corrodes very aggressively, but it actually does. Cadmium, zinc, these are things that are, and magnesium especially, which is why it doesn't make a good material for structural applications. These things are just looking for opportunities to react. They're much more active species. This is why we use zinc as often a sacrificial layer, because it's much more cheaply available, and it tends to work very well without hugely compromising the mechanical properties, and in the way that something like magnesium might. It also doesn't have the same degree of dangers of igniting as something like magnesium does. So there's a lot of application and range to what this says. So there are a lot of different forms that this can take. So what does it look like? How does it look? How does it behave? What are some of the factors that go into it? Stress corrosion is something that happens a lot of times, especially where there's tensile stress present. We'll look at an example or two of this where you can see what's happening as there's tension created in the material. So we'll look at something like a flanged pipe that has stress corrosion evident, and we'll see what effect that has on not only the pipe material itself, but even the actual bolts that are holding together the flanges, and things that we don't always normally think about in those contexts. So there's erosion type corrosion. So this is some kind of chemical attack in addition to mechanical wear. So something like a pipe elbow, something that has a much higher friction for the fluid flow. Anytime you change direction, an elbow is going to corrode at a much, much higher rate than a straight section of pipe or tubing is going to under the same exact conditions, because you have a number of different mechanical things happening there. Think of the kinetic energy of each individual molecule passing by and pounding into the sidewall of the elbow over the course of gazillions of gallons of fluid flow. That's going to create erosion no matter how resistant your material might be. It's going to just mechanically wear out. Every time there's impacts, there's chances of knocking some of that material off the surface, and you have erosion over the course of time just because of probabilistic statistical mechanics and chemical attack on the surface. Over the course of enough time creates the conditions for significant erosion, even with erosion resistant materials. Similarly, pitting is something that you've seen probably a lot of examples of. It's especially an issue in circumstances where there's been some sort of electrochemical pairing between something and its environment, between a material and its environment. So whether it's sitting in ground soil that has some sort of ion exchange happening, pitting is something that also happens in very high sea salty air areas. So near the coastal areas, there's a lot more sort of pitting like this. There's a lot of different examples where anything involving salt water creates conditions for pitting, but there's also crevice type. So anywhere where there can be confined spaces, you get trapment of moisture that acts as a universal solvent and just erodes away underneath. So this is an example image taken of some rivet holes. So just under the head of the rivet, there was corrosion in the material. So any moisture trapped underneath that rivet starts to sort of erode away at the underlying material. And this is why something like rivets can, over the course of time, actually pull themselves out and become an ineffective fastening method if the surfaces aren't properly protected. And even if the surfaces are protected, you can have that showing up. The galvanic type corrosion are dissimilar materials that have some sort of electrolyte in the middle, usually water in the form of rain. So even though rain doesn't always necessarily contain a lot of ions, salts, and other things, there can be examples of acidic rain and things where the rain is pulling other components, solubilizing gases and things from the atmosphere. Certainly that's a thing, and that's present in a lot of the smog heavy areas of the country and of the world. But the galvanic pairing allows for liquid that creates an electrolytic path in order for the metals to exchange ions. So just like in the example of that hydrogen electrode, and looking at the examples of that battery, that battery type arrangement, you have the pairing where you have dissimilar standard potentials creating a path for galvanic interaction. There can also be intergranular corrosion. So corrosion where there's precipitate particles formed. This is something that you might see on aluminum, especially because of some of the kinds of reactions that aluminum can have. You can have different kinds of precipitate form, and often with aluminum that'll result in kind of a white powdery kind of surface as it gets to be oxide toward alumina, which is a fine white powder. So there tends to be a lot of different ways that this kind of intergrain boundary can be used. There's also selective leaching. This is one that it does happen. It's kind of an interesting process because we think of corrosion as being non-selective, but in fact it often is very selective, and it's driven based on the thermodynamic differences that we saw in the EMF table. So if there's a difference in electromotive force, you always have something trying to cause corrosion going in a specific direction. This selective leaching happens to be something that allows for something like zinc to be pulled out from copper brass material or something of that nature. So one thing is selectively pulled out by the corroding process. There can also be much more uniform attack, which is more of what we think about when we think of like metal or steel, specifically rusting. That's sometimes a little bit more uniform, but not always. So there's a few different ways that this can show up. So up here at the top right, we have a stress corrosion crack that's formed along this pipeline, and you can actually see the bolts themselves have actually had a stress corrosion crack as well. So it's not just constrained to the actual pipe wall itself, but even the flange itself is coming apart. So this is an example of a severely damaged pipeline that very likely caused a leak and would have been very highly dangerous. So it would have been able to leak flammable gases or lose high volumes of liquid without being able to trace it very easily because it's not above ground. When you have selective corrosion, you have things more like what's on the left side here. So different versions of galvanic corrosion. So things between where we have a couple bolts and nuts and maybe a washer with a slightly different material. Those different grades of steel, different carbon contents being uncoated, not being a galvanized washer or something. So even if this part of the frame is some sort of a zinc coated steel, the washers themselves being an uncoated steel is enough to have created with the presence of water. And I can't tell immediately whether this is something like the side of a boat trailer or what it might be, but even sitting out in the rain, you create this kind of erosion process by having those dissimilar materials and having a galvanic difference between the standard potentials. Similarly, something like this water pipe under a house, this appears to be copper. Usually when you see a blue oxide, that's a good indication that there's copper present, a blue-green color. You saw the copper sulfate solution that was a very deep cobalt blue color. So copper pipe that's corroding because it's paired with this steel hanger, and this appears to be up underneath a house. This pipe is corroded probably very much to the point of leaking because of the dissimilar potentials between the steel and the copper pipe. So had this been insulated with a rubber layer or some other sacrificial insulator, something that prevents direct ion exchange between these, there wouldn't have been this level of corrosion. So similarly, maybe you have a zinc type steel nut on this side and you have a mild steel nut on this side. One gets corroded while the other doesn't because of the dissimilar nature of the two materials. That can happen very commonly. So you see sort of the white oxide layer around this, but you see the very heavy corrosion around what was probably a mild steel part. Here, fairly typical example. This looks like a part of a frame for the vehicle or something of that nature. So you have a pairing of different materials. You have a bolt of one grade of steel, probably uncoated, maybe a much higher carbon content, maybe higher prone to corrosion. And you have a coated surface, but you have some probably salt water or salt water vapor that has promoted corrosion on this surface. So there's a lot of different factors that may come into play for something like this, creating a difference in electrical potential between them, and with the presence of any moisture at all, being able to having a pairing of that nature. So different regions of the country are prone to very significant differences in corrosion grade. So the really high temperature, more arid climates, typically in these regions, are very lowest corrosion range. So C1, C2, highest corrosion range, getting into sort of the orange and red. A lot of the coastal things, some of the areas in California are moderate instead of severe, but a lot of the areas, especially along the Mexican coast, down into Cuba, Florida, and the Keys, and all those things, all of these are areas down around the coast of Louisiana, Gulf Coast of Texas. Those get into the C4 zone, and C5, I think you get down here even farther south. So really aggressive corrosion in those areas. So just depending on where it's serving, right, where the material is serving, very hard on equipment, especially as you get right along the coast. A few hundred miles inland, you're dropping typically 1 to 2 grades almost in terms of the process. Interestingly, up in the northern region, there's almost none of the same degree of severity as it is in the southern region. So down here at the very southern end of Florida, it's much more severe than up here in Maine. And that's partly because of those lower temperatures on average. All of the days of the year, the temperature here is a lot lower than this, even though the saltwater environment is very similar here versus here. The temperatures are so much lower compared to Florida that you have huge rust issues. And so keep that in mind if you're buying vehicles, especially from any of these states down in the lower region. You might pay attention to, you might see surfaces on parts of doors that have just eroded away and there's nothing left. This is kind of a side view of some of the different types of corrosion. So if you have a more noble metal, you can have galvanic corrosion where it eats away at the base. Flowing corrodent is very common. So just simple erosions mechanically impacting and then stripping away atoms by atom over the course of time. Fretting can happen where you have cyclic movement of materials and you have some kind of a load. So that one's one that's a little bit less common for what we see, but you can also have metal, non-metal, and you have crevice formation at the interface between those, especially where you get pooling liquids and things that help facilitate that. Pitting, so generally removing material and creating typically sort of circular pits in nature. Exfoliation can be layers peeling off of the top, just like named for the exfoliation of skin and skin cells, things sort of sloughing off the surface. So you see a lot of exfoliation type corrosion when rust forms in mild steels, so something that's uncoating. See a lot of this where you see flakes and layers of flakes, but they're always stratified like this. Dealloying can be selectively pulling elements out. So acids might only solubilize one of the components of the alloy, making it very weak. So it can sort of resemble pitting, but on a smaller scale. So it's a little bit different. And then intergranular can happen as well. In the case of tensile stress, you can have stress corrosion cracking. So you have not only the chemical aspects present, but also the physical stress. And then cyclic stress can create something that looks very much like stress corrosion, but they're going to be less tree-like in their forms. They're going to be a lot more just crack-like. So single long stress, cyclic stress, corrosion, fatigue is where you're going to see that as an example. Prevention of this is sometimes complicated, sometimes uncomplicated, depends on what it is. A lot of times we're trying to pick the material based on the corrosive environment or non-corrosive environment. We're trying to pick based on what we know we're going to need for the end application. Nickel is great in a lot of different cases because of that, but it doesn't have some of the same strengths as steels and other materials. and it can be more expensive. So we want to try and use sometimes metals that passivate. So in the case of something like the industrial buildings that you see where they've tried to rust the material immediately upon the structural build of the building, you're doing a lot of things that are creating an oxide layer that shows what the corrosion looks like. So the metal happens with, you have a underlying base metal, and then you have an oxide layer that forms on top. So that's that rust layer that forms on that industrial steel that actually protects it from further erosion of the base metal. And so that's a strategy, is instead of trying to fight the corrosion, let's set up the corrosion such that it now corrodes much more slowly over the course of time, and now it has a much more uniform appearance, instead of allowing it to rust and have discolored different colors and all sorts of things. So having some of the yellow rust and some of the burgundy rust, so they're uniformly rusting the surface so that it has a specific look, instead of allowing it to happen naturally where there's going to be some variance. So you can lower the temperature, but you can't just sort of move everything up to Canada in order to prevent corrosion and oxidation. You can also apply physical barriers, films, and coatings. Those are very, very common. So this is why we paint cars. It's not actually because we want them to look prettier as much as it is we are trying to protect the underlying base color. And that's very, very important. So corrosion prevention, you want to add inhibitors. You want to slow down the oxidation reduction process by removing reactants, so eliminating oxygen from the environment. If it's going to exist on Earth, that can tend to be pretty difficult to do. Or you can attach other species to the surface. So this is why we do different kinds of plating of materials. So gold plating of electronics, in order to both prevent corrosion and improve conductivity, all of those sorts of things. That's why the really thin plating layers on the electrodes in your really, really cheap Chinese charging cords tend to wear away very quickly, and then you have nothing left to actually conduct a charge. And so they keep selling you more by selling you garbage quality in the first place. So very thin wear layer. There is no oxidation forming there. It just physically, mechanically wears away. And then there's cathodic or sacrificial protection. This is used in a lot of applications, especially for things like protecting steel pipelines. So you can't realistically make steel service pipelines out of gold, right? That would make the project completely astronomical in cost. It's completely unreasonable to even think that that would be an option. So instead, it's cheaper to have these large magnesium anodes that you then are applying a current across. And what you can do is by holding a current constant in that circumstance, you can protect the underlying steel from actually corroding. So there's a bunch of benefits to those that allow you to maintain function and operation. And prevent your pipeline from prematurely degrading. It's just something that has to be watched pretty closely. So the galvanized steel instead takes zinc and adds zinc to the surface of the steel. So you have a zinc coating, and what that does is the zinc interacts and corrodes in lieu of the steel, and it takes a lot longer for the zinc to corrode, so that the steel underneath is protected for much longer time. So zinc coating is very, very common. It's fairly inexpensive, and that's why we use it in so many different materials. So this is kind of a diagram of what it looks like for the pipelines. So you have these, you have the pipe itself that is being forced to be cathodic by the difference in voltage between from a rectifier and between the anode and this pipe. So what it's doing is it's basically creating a reversed electrical potential difference between the pipe and the anodes, so that the anodes get corroded and the pipeline gets protected. So you have to periodically replace these anodes. They get worn out as soil conditions adjust and change. The rates of corrosion change, so you have to monitor these stations and monitor what the sort of the current it takes to maintain these voltage differences is. So there's a lot of things that go into protecting the pipeline infrastructure by this way, and it's used in ships as well. So you'll see ships, docks, metal, oil drilling stations, all sorts of things. They'll use this sort of anodic protection so that they can prevent the corrosion of the material. So instead of trying to let the corrosion happen and oxidize the surface, that can be very, very bad in a seagoing vessel. So they use that same protection strategy. So wrapping up the concepts from this chapter, the metallic corrosion is an electrochemical reaction. So it has to do with oxidation or loss of electrons, and reduction or gain of electrons. And as those electrons are consumed in the reduction reaction, you have other things formed. You have those hydroxide ions formed. So it's important to understand where they're going, what they're doing in the process, because those free electrons or free protons can really do a lot of damage to the structures that we build. So these metals are ranked based on both the galvanic series and then the standard electromotive force. So it gives us an idea how likely are they to react, how extreme do they react, how much electromotive force is there between them. So there's a large difference between the things at the two ends of the EMF spectrum. And so if you put those two together, the higher the difference between them, the higher that standard potential difference is, the more aggressively they're going to corrode, and the more quickly they're going to create a galvanic path. So temperature and solution composition definitely affect the corrosion rates, as well as there are different forms of corrosion, and we need to be paying attention to what materials we're picking, what kinds of operating temperatures they're going to be in, what kinds of physical coatings or inhibitors we need, and whether or not we might need to use cathodic protection for something like a structure that's designed to be in service for a long period of time. So there's a lot of design considerations that we have to incorporate. Oxidation of the atom. So this is a few example problems that we want to be mindful of. There's a couple different things that we need to be able to kind of pay attention to. So oxidation of the atom, again, is loss of electrons. We have reduction that takes place at the cathode. So reduction is at the cathode, oxidation is at the anode. That way we can kind of keep everything in mind. So think back to some of your Gen Chem principles, and hopefully you had a good instructor that was hammering some of these principles home. So if we have to pick, an overall electrochemical reaction must consist of at least what? A single reduction reaction is what's called a half cell. A single oxidation reaction is another type of half cell. That's why I wanted to show you guys the video to see physically, unless you have both the reduction and the oxidation half cells, a pair of half cells, you do not have a whole cell, and you do not have an overall chemical reaction. You just have two things in solution and nothing happening. That's fundamental to understanding this electrochemical process. So another example here, one of the problems where we do an actual calculation, because we didn't cover a lot of formulas, I wanted to include this. So a piece of a corroded metal plate was submerged, was found in a submerged ocean vessel. So it was estimated that the original plate area was about 12 inches square, and they weighed it approximately 2.1 kilograms. So that's what they think the original weight was. It had corroded away during the submersion. So assuming a corrosion penetration rate of 249 mils per year, thousandths of an inch per year, for this alloy in seawater, estimate the time of submersion in years. Assume the density of the metal is 7.6 grams per cubic centimeter. There's some wonky stuff that happens with units when these calculations are done. When you're doing calculations with an area in inches, you use one value for K, the constant. When you do it in, I think it's square centimeters, you do it in, you calculate K differently. And so we'll look at the calculation. So the first step is to understand what the formula is for the CPR, or the corrosion penetration rate. So that's this constant K times W, the weight, divided by, all in the bottom row, the density times A, area, times time. So rearranging that for time, doing some quick algebraicy, you have our new equation. And for the CPR in terms of mils per year, you can calculate what K is if you rearrange things. So that weight divided by that weight converted up to grams from milligrams, divided by your grams per cubic centimeter, and then number of cubic centimeters per cubic inch. We have 2.54 cubed, and we have the area in inches squared times the factor of 1/1000, because we're trying to get to thousandths of an inch in order to balance out this constant. So we're dealing in thousandths of an inch. We have 1 day, 24 hours, 1 year, 365 days, unless 2020 was worse to us than I thought. And so we get this constant that we calculate out because the masses drop out and some of the other things. The constant is just a constant. It's just a number that is 534.6. So we take our 534, we plug that in for our CPR. If the units are different for area, we get a different kind of number. And that's why we want to pay attention to which constant do we use, because this constant, when used in combination with kilograms, and we convert up from kilograms to milligrams, so we've got to make sure the mass units are going to cancel out. Even though the density is in grams per cubic centimeter, the way that this is done as a calculation is trying to get units to cross cancel and blending the metric system together with the imperial system is a very frustrating exercise. But you're given the constant in mils per year, so thousandths of an inch, so you have to deal in inches, and then we get 49,380 hours, so we convert that up from hours to years, and we get 5.64 years under the salt water. In order to have a size change in total area to what we have with the final sample. So another example is looking at 5 different metals. So we have our electrons, so that's what's supposed to be represented here in the question marks. So we have the gold, so it looks like the way this came across, this is doubled, but it's gold 3+ and 3 electrons yields gold. And so it's just trying to duplicate this here with confusion from the table, because pasting from PDFs doesn't always work cleanly. So you have a potential for gold in terms of in order to get the electrons added back in. So this is a difference of 1.4 volts. There's a difference for copper. So copper 2 and 2 electrons going to copper of 0.34. So nickel minus 0.25, iron minus 0.4, sodium minus 2.9. So sodium really loves to be in the ionic state. Gold really does not. You really have to push it very hard to the other side to be able to strip it of its electrons. So it's saying which of these metals is the most reactive, and the most reactive is the most negative. So remember, more negative potential, more active. The least active by far, by a wide margin, is gold. Copper, fairly active. Nickel and iron, progressively more active. And then sodium, extremely active. So the most reactive species based on the electrical potential is sodium. So we have another one. This is a good example to go through as far as calculations for you guys that I think will be really, really helpful. So this gives us a table of weights and times. So this is actually mass per area. So this is a mass. This factor is a weight normalized by area is what that's called. So weight divided by area. This is what W is. What we're looking to do is determine the oxidation kinetics. So does this follow a linear pattern? Does this follow a parabolic pattern? Does this follow a logarithmic scale? So we have, and then we want to know what is W after 3,500 minutes. So 1.9 at 25 minutes, we have 3.76 at 75, and then 6.4 at 250. So we look at these different equations. So linear is some constant times time gives us W. Parabolic is the square of W is proportional to K1 times some time factor plus a coefficient. And then our logarithmic expression is W is some constant times the log of K5 times time plus K6. So a logarithmic adjustment to an initial fitting constant. And those are the ways that we represent them mathematically. So what does this data fit? Well, if it's something like 2 at 25 and something like 4 at 75, so this is 3 times, this is 2 times, you would expect something like a 3 times and 2 times relationship. Well, 3 times 75 versus 2 times 3.5, we're less than 2, and we're on the order of 3 times here. So what we can see is we're way less than 2. So we're not progressing linearly. We're not moving in a linear scale anymore, because this should be a much larger number at 250. So especially to go from here 10 times, we would expect this to be, instead of a little bit less than doubled, we would expect this to be well more than doubled again. We would expect this to be something like 10 or 12 almost. So this is not behaving linearly, and it could be behaving parabolic. The only way to really tell for sure is to try and solve for a given W using a couple different coefficients. So you set up a pair of equations, or you set up 3 equations, 3 unknowns. So you have a K1, a K2, and so on. You solve for these coefficients and then see if the coefficients line up. If they don't, then you don't have a good fit. So it's the same thing that you would do if you would take this and plot it, try and do a fit and see if a second order fit it will kind of look close, but then one side or the other of the data will be very far off. So its predictive power will not be very good. So what we're going to end up determining is we're going to end up determining based on this. We rearrange our expression here for a more algebraic exponential form. So 10 to the w over k to the fourth, or w over k4. So this is our exponent here, just like it shows in the formula. This step gives us, we have a t1 and a w1. We have a t2 and a w2. We have a t3 and a w3. And we're looking for k4, k5, and k6. So we go through the algebraicery in order to give us the values. 6.5, 0.03, and 1.1 is our approximate values for these k's. So you have to do some rearrangement for these, but you will have to do this kind of problem. You will have to solve these sorts of things for the examples in the homeworks, and you might see something like this in one of the tests. So I wanted to give you an example of that. So it's fairly straightforward algebra. It's just something we have to do all the time. So a last problem example here is going to be looking at an electrochemical cell. So a pure nickel and pure iron electrode immersed in the solution with divalent ions at room temperature. If the concentration of these two, and they could change out the molarity, they could change out all of these different things. So looking at two completely different molarities of solutions, we're looking to see what voltage is generated at 25C. So this is, again, a basic chemistry question. You've seen examples of these from long ago, but the concept here is the same. So you're looking to see, okay, the respective reduction potentials they nicely gave you there for nickel and iron are minus 0.25 and minus 0.44. So remembering the reaction here is iron becomes iron 2 plus 2 electrons. Nickel is nickel 2 and 2 electrons become nickel. Nickel 2 and iron together become nickel and iron oxide. So this is our set of chemical equations that are expressing what's taking place. So our formula looks like that potential difference is the V naught for nickel minus the V naught for iron. And we subtract from that our adjusting factor of our coefficient divided by 2 times the log. And this is given in a little more detail in the text, but this is the simplified form that we're using. So log of the concentration of iron 2 divided by the concentration of nickel 2. So minus 0.25, subtract from that our minus 0.44, because even though it's already negative, we're still doing a double subtraction there. So we always look at the difference between the two potentials, even if they're both negative. And subtract our solution out times the log of the ratio of the two concentrations. So the natural log of our 0.4 divided by 0.002 to give us what we're looking for. So I'll leave it to you guys to figure out what the correct answer is. And then you'll see why that potential difference might be good for being able to prevent corrosion by combining nickel and iron together. So we'll leave this part here. This is the end of the lecture for just the chapter itself. A lot of the concepts, a lot of the questions and things in the homework are concept questions. There's some problem questions, and I think we've hit some good examples of each of those. So I'll pause here, and then in a couple of seconds we'll re-gear to discuss some of the material selection and things thinking toward the materials website that you guys will be working on later for the MEs, and more immediately for the METs that are going to be working on material selection. So before tuning into that part, I want to make sure everybody gets a chance to go have a happy Thanksgiving. So with that, we'll pause and then change gears. All right, so welcome to the next section of this. For choosing materials, one of the things that is very useful is an Ashby plot. What is an Ashby plot? Well, sort of anything you want to a degree. The Ashby plots, what these do is these collect two different axes of information on a log scale. So this allows us, depending on what we're trying to pick based on, we plot something like Young's modulus versus density. And I'll increase the size of this to make it a little easier to visualize. There are different regions of material that have different options within the material. So foams generally are lower in the Young's modulus versus density. So very low density, very lightweight, but also very low Young's modulus. Natural materials, woods, things like that tend to be a little bit higher in density and Young's modulus. Elastomers, very low Young's modulus. They're very stretchy, but they tend to be much more dense than foams, which makes sense, right? Polymers are above those, somewhere in the mid-range. Metals are up here, very high densities and very high Young's modulus. Ceramics even above that, so the materials aren't moving very much relative to stress, whereas foams move a lot relative to stress. So do elastomers move a lot relative to stress. So less movement relative to stress, the higher up you go because of Young's modulus. The lower you go, the more movement you've got. So for a bridge, elastomers would be absolutely terrifying. That would be a really bad thing. Imagine the bridge dropping by as much as a 20-foot height if you built something out of elastomers. That would be death-defying. Whereas you wouldn't necessarily want to make them out of composites because of some other different materials properties, like their tendencies to fracture under sudden impact loading, whereas metals tend to be a little more forgiving. So the technical ceramics are up in this range. So there's a lot of materials, diamond up at the very, very top nearly. So there's some nickel alloys and steels and combinations, and there's some overlap between the metals and the ceramics in this range. So this is still a Young's modulus. This is just identifying some different examples. So cork, flexible polymer foams, EVA foam is up at the slightly stiffer end. So this is increasing stiffness and decreasing stiffness going down, increasing density. So heavier and heavier and heavier materials per unit weight. So concrete is somewhere in here. So metals are even heavier in terms of relative density at the same strength than concretes. Should tell you why we build a lot of stuff in concrete. There's also some really interesting composites. So carbon fiber reinforced polymers versus glass reinforced polymers. Carbon fiber reinforced are much stiffer. Magnesium alloys, much lower in density, but also lower in overall stiffness compared to tungsten or even copper, interestingly enough. So a lot of different things that you can identify, and depending on what you're looking for, you need a certain level of strength in order for a specific application to be met. And so if you're trying to build something, I'll go through, there's actually a really helpful example video that I'll play that covers how this is used in a design selection process. So what I'm going to have you guys do as far as the in-class discussion piece of it, we're going to use this as the in-class discussion and say, okay, now we're going to look at the strength, the actual sigma versus density. So this is a what's referred to as a level 2 chart. So foams, very low strength, very low density. Higher strength to density ratio gives you more performance. So in terms of overall strength, you're not necessarily getting with something like a carbon reinforced polymer, you're not necessarily getting a lot more out of a lot of metals. And sometimes you can actually get even more strength out of certain carbon fiber materials than you can out of a lot of common steels. So a lot of steels are going to be much lower in this range. Concrete, however, is very heavy, but not very strong compared to some other materials. So a lot of polymers, especially like engineering grade polymers, PEEK and polycarbonates and things like that, PMMA, these are things that we can build stuff out of that are fairly lightweight, but also fairly strong, and that's why we do that. Wood, of course, because of cost and other things, we'll look at on the next chart, can also be a factor. So an Ashby plot is comparing some property of a material on a log scale with some other property of material on a log scale. So remember, every step you take up in terms of density, it becomes hugely heavier, significantly heavier than the previous item. So titanium, super strong, super lightweight. Tungsten, super strong, but a lot heavier, significantly heavier. So tungsten carbide, great for tooling, really heavy material, really dense. Diamond, a lot lighter. This is why we use some of that industrial diamonds in tooling as well. So alumina, very, very commonly used. So alumina actually as a ceramic is pretty tough stuff. Not to be confused with aluminum. These are aluminum alloys. So alumina is a ceramic, aluminum is the metal. Very big difference there. So the aluminum alloys are fairly lightweight. They can actually get to be pretty strong in some of the same ranges as some steels. Zinc alloys are a little heavier, but they're also corrosion resistant and all of those things. So there's a lot of range. Silicon carbide, really tough stuff. Silicon nitride, so nitride coated things. Titanium nitrides are way up here in these ranges. So a lot of different nitride ceramics are very, very tough. So glass is going to be somewhere down in the lower regions. Polyethylene, polypropylene, very common for like water bottles and things of that nature. So reasonably strong, proportional almost to a lot of kind of woods, not necessarily for all the polyethylenes, but a lot of polypropylenes are a little bit stronger. And something like butyl rubber down here, kind of tough, not super dense, but a lot of woods are also down here. So there's a second group of like hardwoods that go up in this range. There's softer woods that come down here into the same range as foam. So your balsas and things are going to be down in that range. You can also plot it versus relative cost per unit volume. And what that does is allow for the things that are hugely more expensive, tungstens, carbides, a lot of those things, some of the metals can tend to be outrageously expensive. Some of the steels and carbon steels and things are much less expensive, only a little bit more expensive than some of the foams and some of the woods, which are very low in terms of cost, and then concrete being the cheapest. Aha! And now you know the real reason why on an Ashby plot we would select concrete. You make stuff thicker and add in other materials to make it behave more like a composite. So concrete reinforced with fibers is going to be higher in term, or reinforced with steel is going to, and rebar and those networks. It's going to be a lot stronger, but it's still going to be less expensive than some other things. So stone, brick, those sorts of things. These are why, depending on availability, brick walls have to sometimes be a little bit thicker maybe than composite walls made of wood. Stone is similar. The stone is a much narrower range of strength. Rock kind of behaves like rock, weirdly enough. But there's different densities of those, but they all kind of have similar mechanical properties. Same thing with bricks. They kind of do what bricks do, and that's all they do. Rubbers are a little bit more narrow for butyl rubbers, neoprene rubbers. Silicons are more expensive. Neoprenes are often used for like exam gloves. A lot of kinds of seals are neoprene rubbers rather than butyl rubbers. They can be much stronger. Nitrile rubbers and things are the same kind of way. They're more expensive. But a lot of the polymers we use, polyethylene, polypropylene, polystyrene, PET, it's what a lot of disposable clear plastic bottles are made of, PET. So pretty tough stuff, pretty inexpensive relatively, but tougher than some of the other materials. That's why we use it so commonly, because you can use less of it, get a better result. Aluminums are sometimes actually more expensive than a lot of carbon steels, weirdly enough, especially high grade aluminum. Cast irons are less expensive than steels, but weaker and inexpensive, so processing cost goes into that. Composites get to be more expensive than a lot of common metals. So galvanized metal, a lot less expensive than, for instance, carbon reinforced polymer, which is up here. So nickel alloys, pretty tough stuff, but way more expensive. And that's why we don't use that in more structural applications. Whereas PEEK, this stuff way over here, this is a wild material to make stuff out of because it's very low density, right? So it's over here with a lot of the other plastics, but actually gets you performance that's starting to get into almost the range of some of the steels. You can see here, almost into some of the range of, you're not quite getting into titanium level, but you're definitely getting into much more serious composites. You're almost crossing over into some territory of some glass reinforced polymers, and there are versions of PEEK and things that are glass or carbon fiber reinforced, and that's why these are up here with almost some ceramics. So really, really hard, stiff materials that do not bend and flex, and that can be great in some applications. So this is what the Ashby plots tell you about a material, because you can't just pick based on, oh, well, I want to make everything based out of carbon reinforced polymer because it's the best. It may not be the best for your application and may not be the best in terms of cost efficiency. So all these things have to be developed, and that's part of the reason why I think this is such a great example. So I'll go ahead and cover this one. Let's see. Yeah, so we'll go back to the beginning of this one. It's actually a pretty comprehensive example.
Hi, I'm Dr. Billy Wu, and today we'll be talking about how we can use tools such as Ashby plots and performance indices to help us select a suitable material for a specific application. So why is material selection important? Well, let's take the example of a bike. When designing a bike, we might first think about the design criteria or what people care about. This can include things like cost, weight, strength, stiffness, aesthetics, durability, manufacturability, and more abstract factors such as the feel of the bike. Then, if we think about what materials are available to us, there's an even greater list of possibilities ranging from metals such as steel to composites such as carbon fiber reinforced polymers and even natural materials such as bamboo. If we have a look at the market, we can see that there's a diversity of bikes out there which already use a whole range of these materials. Therefore, the question is, which material should we use, and are there any design tools which help us to make these decisions?
If you're looking to start or grow a business as a coach, therapist, or course creator, listen up really quick.
To solve this problem, let's look at an example. Let's say you're a passionate cycler, not quite a professional, but proficient nonetheless. You're looking for a new bike, but you can't find the right one that's perfect for you, so you decide to make your own, which is high performance, but also affordable. If we first think about what we care about, or our design criteria, there are three main things. Firstly, weight. We want to do some hill climbs, and having a lighter bike will help with this. Secondly, stiffness. We want to transmit the power in our legs to the bike in the most efficient way, and we don't want the frame bending. And finally, cost. We want a nice bike, but at the same time, you want to make it affordable. If we then start to analyze the stresses that are found on a typical bike, the problem starts to become quite complicated. Therefore, in the initial design stage, we want to simplify the problem as much as possible. Here, we've assumed a cylindrical rod of length L, which is held at both ends. A force F, which represents the rider, is applied at the center of the beam, which causes a deflection, delta. Now, if we look up the mechanics equations related to this problem, we can see that the central deflection can be given by FL cubed over 48 EI, where E is the Young's modulus and I is the second moment of area. Next, if we then consider the mass of our cylindrical rod, we can define this as pi r squared, which is the area, times by the length to give the volume, times by the density ρ to give the mass. We can then rearrange this equation to make r the subject. Then, if we bring back in the deflection equation and then substitute in the moment of inertia for a circle, which is given as pi r to the 4 over 4, we come to a combined form of the equation. We can then substitute in the equation for r into the deflection equation, simplify, and then rearrange for the mass. If we have a look at the various terms in the mass equation, we can separate these into two types. Firstly, there's a set of geometric and load parameters which are governed by the design of the bike. Secondly, and more importantly, we have properties which are defined by what materials we select. If we then take these material parameters and think about what we're trying to achieve, we'd like to reduce the mass, and therefore having a low value of ρ over square root E would achieve this. Conventionally, we want to define a performance index, which we maximize. So what we'll do here is flip this upside down to give our final performance index P, which is equal to square root E over ρ. Okay, so now we have our performance index, which we define as square root E over ρ, which we want to maximize. But how do we use it to help us select a suitable material for our bike? Firstly, let's consider an Ashby plot, which is a visual way of plotting two material properties against each other. In the case you see here, we have log of the Young's modulus on the y-axis, which represents the stiffness of a material, and on the x-axis we have the density. Also labeled here are a few material families such as foams, polymers, metals and composites, as well as a few selected materials from these families. Now, if we return back to our performance index equation and rearrange this, we can start to down select materials for our application. If we take logs of both sides of our performance index equation and rearrange this into the form y equals mx plus c, we get the equation below. Now, what this tells us is, if I draw a line with a gradient of 2 on my log Young's modulus against log density plot, all the materials along the line will have the same stiffness performance index. To get materials with a superior performance index, we need to move our line up to have a higher y-intercept. So, if we take that principle, and from the three design lines shown in the Ashby plot select only materials above the top line, we can reduce the initial 69 materials to 19. In doing this, we've eliminated all elastomers and polymers from the selection. This makes sense since these materials generally have a low stiffness for a given mass. However, you can see that some materials with a very low Young's modulus are still in the analysis, such as foams. This is because even though these materials are very flexible, their densities are very low, which give them a very good specific stiffness. However, in practice, it's unlikely you'd want to make a foam bike as you need an impractical amount of material. So, in order to further filter the materials towards practical selection, let's return back to our original governing equations. In the original example, where we simplified the problem to a beam supported on either end with a centrally loaded force, we can define the deflection as a function of the geometry, force, and Young's modulus. If we then rearrange this equation, we can make the Young's modulus the subject. Then, we can put some assumptions into our analysis. For example, let's assume that the maximum force is 1000 newtons, the length of the beam is 90 centimeters, the radius is 4 centimeters, and the maximum allowable deflection is 1 millimeter. If we put these numbers into the equation, we can get a lower limit for our Young's modulus, which is 7.6 gigapascals. Finally, if we eliminate glasses and ceramics from our analysis, we get to 6 remaining materials, which is much more manageable to do an in-depth analysis. So, if we now take our 6 remaining materials, their Young's modulus, and their density, we can calculate their stiffness performance index and rank them. Here, it can be seen that carbon fiber reinforced polymers rank the highest, with natural materials such as wood and bamboo surprisingly following, and ahead of materials such as magnesium and aluminium alloys, as well as glass fiber reinforced polymers. This is already really useful, however, it's not the whole picture. So, earlier, our design objective was to make an affordable high-performance bike, and whilst carbon fiber composites are very fast on the road, they're equally fast in taking money from your bank account. Therefore, we need a way of factoring in the cost of the material. Now, whilst we could just incorporate the cost of materials into a new performance index, it's often better to use normalized cost of a material relative to low-carbon steel. The rationale for this is that material prices fluctuate over time, and therefore the optimal solution will depend on when you do the analysis. However, the relative cost of materials in theory varies less than their absolute values. Thus, taking the normalized cost of a material relative to low-carbon steel, which has a very stable price, can give much more consistent answers. Now, if we then take the performance index of our 6 materials and incorporate the normalized cost, into the performance index, we can re-rank them. In this case, we put the normalized cost as the denominator, as a lower cost would increase the performance index. Also, we've arbitrarily put a unity weighting on the cost performance index, but if this was more or less important, this would obviously change the eventual answer. Now, after factoring in costs, we can see that wood, aluminium alloys, and bamboo are the top materials, with carbon fiber second to last now. Therefore, does this mean that we should all make wooden bikes? Invariably, the answer is no. If we look back at our initial design criteria, this included a long list of factors, and in this analysis, we only considered the cost, weight, and stiffness. One could repeat the analysis to look at strength of the material, and we would come to a slightly different answer. However, one of the more difficult factors to account for in these performance indices is often the manufacturability, which also affects the overall cost. Whilst we have factored in cost from a materials perspective in this analysis, it does not include the cost of manufacturing the materials into the final form that we want. Wood, for example, which is highly ranked, would need to be cut into the desired shape, whereas metal can often be manufactured at low cost through an extrusion process. Assembling the frame is another complexity. Metals can often be welded or brazed together, but wood needs to be glued together, which requires longer setting times. Carbon fiber components require a mold and a layout process, which is often very manual and requires costly tooling. Therefore, whilst the Ashby plot and performance index analysis is useful, other factors, especially manufacturability, need to be factored in. This can of course be added as an additional filter in more advanced analysis, but hasn't been done here. So, to summarize, there are a lot of possible material choices when designing a product. Tools such as the Ashby plot and performance indices can help to narrow the design space. But we shouldn't just consider a single design factor, an optimal choice is often a combination of multiple factors. And quantified analysis does help with decision making, but we need to consider the practical implementation of our designs with key factors such as manufacturability. So thank you very much for watching this video on material selection using.
So this essentially brings us back to the concept of why everybody ends up effectively making everything out of steel or aluminum. So that's not always the right answer, but when it comes to manufacturability and cost, those are the right answers in a lot of circumstances. So what we want you guys to do is think in terms of, and this is two examples of these, two examples of different types of plots. The square root of sigma divided by density is one kind of line that you can use to decide things. The ratio of sigma to density is the one that he was using in that design, and it's fairly traditional because it gives you a straight line fit over the course of these materials and allows you to easily select based on where it is. So you'll have to kind of manually draw on one of these Ashby plots in order to find one that fits what your definition is. But in terms of being able to grab the right material or select the right material for a given application, we'll take a look at the handout for this assignment real quick. So for this pre-project work in pairs, what you're going to be doing is you're going to be doing an example. You're going to do a brainstorming session and come up with what things you're going to need in terms of parameters and things to measure. Think of fizzy awesomeness, since I'll get to do some definition here. Think of fizzy awesomeness as you're going to need to pick a material for a container for fizzy awesomeness, the new replacement for the GCU, the energy drink, whatever it's branded as now. You should probably come up with some kind of definition for what that material needs to be and why. You're going to work on, I'll see about posting some specific questions for you guys, but you're trying to figure out a material that's lightweight, easy to ship, and easier to manage in the context of packaging for something like in-house energy drink. You're going to include an image of an Ashby plot that is relevant and the reference for that, and you're going to justify in a third part, you're going to pick a material choice for a bathroom stool because you want to be able to select exactly how a material is going to behave and what material needs to work there and why. What is the modulus need to be at a minimum threshold in order to hold people up on, say, a 3 or a 4-legged stool? What kind of stiffness, using that same sort of analysis that you saw in the video, where you have a load across a beam, what sort of load does it have to take, and therefore what kind of stiffness does it actually have to have? So what does the Young's modulus need to be at minimum, and then pick a material based on a parameter from an Ashby plot. So make sure that you're using references for what these Ashby plots are. So that should help clarify a little bit about what we're doing in terms of this pre-selection project. And then I'm looking to see, we're going to replace the anodizing aluminum lab. And then for the benchmark, what you're going to be doing is in a bit more detail. So this is something that has to be done individually. You have these 5 questions. So in this case, for this handout, these are the in-class questions, the P1 through 3. I forgot about that. And then 1 through 5 are your project questions that you're working on. There are a couple things that you're trying to understand and specify. So what are the minimal function? What are the requirements? What does the component have to do? What does the constraint have? What is the constraint? What are the things that have to be met? What are the criteria to maximize or minimize? And then what are some of the free variables that you're able to change? So we'll detail this closer when we get there. MatWeb is a really good source for this. Then you need to include all of this detail in the results and discussion. So the material selection process, this is going to be much more in depth, and that's why this is a benchmark. So there's a lot that goes into this one. All right, so I think that gives you guys enough material to focus on for the pre-project, so that you know why you're doing what you're doing, what this looks like, what does the container need to do, what kinds of pressures does it need to contain, all of those sorts of things. It needs to be able to be shipped, so you have to be able to stack these things, all of that has to be considered. So can you mathematically justify why bamboo is a good container for physiosomeness? I don't know. That's up to you and what you can determine based on the Ashby plots, and it has to be correct. So I'll try and keep an eye on messages in the forum and see what you guys need from there. But this should give you guys a pretty good starting point for what you need in terms of the materials. For the MEs that are watching this, we'll get into more detail for the materials website here in the coming weeks. Thanks, and everyone have a good Thanksgiving.